Hello, and welcome to Empowered Learning. This video will be about a technique called integration by parts. We will talk about where this particular technique comes from, the order in which you should use it if you're having to perform integration. We'll talk about a strategy on how to properly pick or parse out your integrand so that you'll know what to select for the formula that we're going to use for integration by parts. And then we're going to go over several examples. So the first thing I want to tell you is that I'm assuming that if you are watching this video, that number one, you're familiar with derivatives. Number two, you're familiar with how to take the general antiderivative of a function. Number three, you have already learned how to use the substitution rule for differentiation. If you are not familiar with those things, I suggest that you watch my videos on those topics. If you just type in, hey, how to take derivatives, substitution rule for integration, antiderivatives, you'll see some of my videos pop up if you're on YouTube. If you are in one of my courses, then of course, all you have to do is look for the title in our virtual course area and you'll see the link for that. So with all those assumptions, I want to go ahead and say that with the substitution rule, we know that the substitution rule is essentially just the chain rule being undone, or the chain rule being done backwards. So the integration by parts is similar in that it is essentially the product rule being done backwards, or the product rule being undone. And so we're going to see how that looks so that we can come up with a formula for integration by parts. And then we'll talk about actually how to use it. So we see here that if I take the product of two functions and then I take the derivative of it, then the product rule just says the first times derivative of the second plus second function times derivative of the first. Then from there, if I was to integrate both sides with respect to x, then of course on the left side here, since we're undoing the derivative by fundamental theorem of calculus, that would just be whatever the integrand is. On the right side, we know that since we have two terms in our integrand on this side of the equation, we can split that up into two separate indefinite integrals. From that point, what we want to do is we want to solve for this particular term here, okay? And we'll see why in just a second. So to do that, what we need to do is we need to subtract both sides by this other term that we don't want over here. And if we do that, we'll see that we end up having the product of f and g minus this term is going to be equal to the term that we wanted to solve for. Now, if we assume that we let our function f of x equal u and our function g of x equal v, then we can rewrite this formula in the way that you see here. So of course we can let this be u. We're going to let this be dv since this is the derivative of our function g. Of course, this is u again here. This is v here. This is v here. And this will be du, meaning the derivative of u, which of course u is equal to f of x. So we see simply here, we just have this form of indefinite integral of u dv equals uv minus integral of v du. And I also have it here in prime notation form because for most of us, that is probably a more convenient way to express it. But you'll see me in this video go back and forth in between the two. All right, so now that we see that we know where integration by parts actually comes from, the next thing that we are going to do is to see how to use it before we get into some examples. So how do we select what is going to be u and what is going to be v? Okay, because again, we know that u is going to be f of x, v is going to be g of x. but in an integrand, how are we going to split it so that we know what's what? Well, simply put, we're going to let our function u, which we're also calling f of x, we're going to let that be the function that is easiest for you to take the derivative of, okay? And we're going to let v be the function, or dv, if I want to be more correct here, because we're going to be selecting based upon what we said here. We're actually going to be selecting what is u and what is the derivative of v. So we're going to select the function that is going to be easiest to take the antiderivative of so that we can find out what g is. Let that be the v prime or the dv. Okay, so that's essentially what we do. Now, in practice, sometimes it's not that easy to select what's going to be the u function, what is going to be the dv function. Other times it's very easy. Sometimes it doesn't matter which one you choose, it ends up working out the same way. And other times when you choose it one way, it works out real easy. The other way, it turns out to be a pain. Okay, so I'm saying all that to say that the only way you really get good at knowing what to pick and when is just to practice. Okay, but I'll try to do enough examples here to where you get a general idea of how to approach some of these basic problems. All right, so let's look at our first example here. So remember that we are going to try to take basically the most general antiderivative of this function, because in indefinite integral, that's what that means. And we look here and we know just by looking at this, we're not going to be able to take the antiderivative of it straight up, meaning just look at it and say, hey, the antiderivative is this. We also know, as far as the substitution rule is concerned, I could use the substitution rule. If I did it, let's just see what it'll look like. Here it would probably make sense to let u equal 2x, which means that my du is going to be 2 dx, and thus this means that 1/2 du is going to be equal to dx. If I did that, then I have a situation here where I would have e raised to the u, dx would be 1/2 du, and I would have to get very creative here and say, all right, well, if this is the case, x is going to be the same as u divided by 2, okay? And so from here, notice that if I do that, what I end up with is 1/4 on the outside, but I still have u raised to the u times e raised to the u du here. So what I've just done is made the problem that was a little more simple to do a lot harder, and I still haven't solved the problem of being able to look at something here and take the antiderivative of it straight up. So we know that using the substitution rule isn't going to work. Now, in the pecking order of things, we know that we start off trying to take the antiderivative straight up first. If we can't do that, then we do substitution rule. If we can't do that, then we do integration by parts. Okay, so we try those out. So in the pecking order, this is option number 3. And we see that options number 1 and 2 haven't worked. So therefore, we know we need to try to do integration by parts to try to do the integration for this particular problem. All right, so I'm going to erase this, and then we're actually going to go through the process of using integration by parts. All right, so when we use integration by parts here, remember that we want this to equal the indefinite integral of u dv. And so that means here I have to pick what is going to be my u, what is going to be my dv. Now, if we look here, we see that it's going to be real easy for me to take the derivative of x, okay? Matter of fact, it's actually going to be relatively easy for me to take the antiderivative of x as well, okay? So this x here could go either way. For the e raised to the 2x, we see here that taking the derivative and or the integral would be relatively easy as well, but I am going to have to use a chain rule to do it. This is one that's pretty well known. We know the antiderivative is e raised to the 2x divided by 2. So we will say that it can go either way as well. Okay. Now, what's going to be the deciding factor here is if I took successive derivatives, which one will terminate. Okay. And so here in this case, if I took the derivative of x, it's just going to be 1. If I took the derivative of 1, it's just going to be 0. If I took the derivative of if I took the antiderivative of e raised to the 2x, I would just keep on getting successive iterations of e raised to the 2x. If I took the derivative of it, I would get the same thing as well. Okay, so the fact that x, if I took successive derivatives, will terminate, I want to go ahead and use that for my u. And so I'm going to explain why that's important a little bit later here. Okay, so we're just going to let u equal x. We're going to let dv end up equaling e raised to the 2x dx. All right, so I'm not sure why my pen's not writing the way that it's supposed to. Okay, so now that we have that, our strategy here is we're going to figure out what du is by taking the derivative of x, and we're going to figure out what v is by taking the antiderivative or the integral of e raised to the 2x dx. Okay, so I'm going to rewrite this over here. And so if I took the derivative of x with respect to x, it will just be 1 dx, or just dx. If I took the antiderivative of e raised to the 2x, this would be e raised to the 2x divided by 2. And so we know that if I say the integral of u dv, according to our formula for integration by parts, we know this would be uv minus integral of v du. So using that formula here, I'm going to say integral of u dv, it's going to be uv times integral of v du. And our u is x, our v is 1/2 e to the 2x. So we'll just say this is 1/2 x e raised to the 2x minus integral of our v. If you noticed, our v here is just 1/2 integral of e raised to the 2x, and du is just dx. Okay. Now, if you noticed here, because we picked our u to be x, notice that the du here really was just a constant times dx. And so that was one of the reasons why we selected u to be x, because we knew that if we were to take the derivative of x, it would just be a constant. And by it being a constant, it makes it a whole lot easier to integrate what's going to be on the inside here. Okay. So now that we have that, we can look at this and say, yep, I know what the antiderivative of 1/2 e raised to the 2x is. I could do that relatively easy. Traditionally, we would use the substitution rule, but we know that this is one of those common ones where if we ignore the constant here, the antiderivative is just going to be like how I said here. It's e raised to the 2x divided by 2. Okay. So with that being said here, we know that the integral of x e raised to the 2x dx, that's the same as the integral of u dv. This is going to be 1/2 e raised to the 2x, and I forgot to write the x here, so I'm just going to write it there, minus 1/2 of integral of e raised to the 2x dx. And of course, the integral of e raised to 2x dx, all of that is just e raised to the 2x divided by 2. Okay, so I'm going to erase this, and we're just going to write that this is just 1/2 of integral of e raised to the 2x in its place. And then we'll add the plus c at the end because this is indeed an indefinite integral. So, aka the most general antiderivative. So if I rewrite everything, it's just going to be 1/2 x e raised to the 2x minus 1/4 e raised to the 2x plus c. And so that would be what the antiderivative of x times e raised to the 2x is by using integration by parts. Now, in showing you this, we're also going to learn another type of strategy for integration by parts, which is a bit quicker, and it's called a tabular integration. And so it's really used for two types of integrals. One is the one like what you're seeing here, where the integral, if we did it in succession, would terminate. And really what I'm saying here is that because we chose u to be x here, and if I keep on taking successive derivatives, I would eventually get to 0. If I had to do successive rounds of integration by parts to this particular integrand here, I would eventually get to where I would have to stop. Okay, so that's one type. The other type would be the kind where the integrals are going to be circular, and what that means is that when we choose our u and we choose our dv, both of those functions, the derivative of it is just going to be a variation of a theme on itself. So for instance, sine, we know that the derivative of sine is cosine. The derivative of cosine is minus sine. Derivative of minus sine is minus cosine. And you see, if we just keep on taking derivatives, we'll just keep on going in circles. Same thing with e raised to the, let's say, e raised to the x. We know that e raised to the x is a derivative of itself. E raised to the 2x, just like we looked at before, e raised to the 2x, the derivative of that is 2 times e raised to the 2x. The antiderivative of it is e raised to the 2x divided by 2. And every time we took a successive derivative of e raised to the 2x, we'll just be multiplying what we already have by 2. If we were to take the antiderivative of e raised to the 2x in succession, we would just be dividing by 2 every time we do it. And so when we have integrals that have those types of functions in them that are being multiplied times each other, they are great candidates for tabular integration because it basically helps cut down on the amount of work that we have to do to get what the final answer is going to be. Now, I'm saying all that because I'm now going to show you how to do this same problem by doing what we call tabular integration. And so I want to go ahead and introduce this now because depending upon the type of integral we're faced with, it may be more advantageous to do it this traditional way, or it may be advantageous for us to do it the tabular integration way. And I want you to be familiar with both ways so that you can use both tools when it is most efficient to do so. So what I'm going to do here is actually do one that is like this. I'm going to do x squared first so you can really see how this works. All right, so before I do this one though, I'm actually just going to do the one that we did first and then go into this one so you'll see how this actually works as well. So I'm just going to draw a little line here and let me change the colors right quick. And so let's do this one first. All right, so if we do tabular integration, we're going to do the same thing as we did before to start off with. We're going to select what our u is going to be, and we're going to select what our dv is going to be, okay? Just like how we did last time, we let x be u, but we're going to put it here in this column, and we're going to let e raised to the 2x dx, let that be dv, okay? Now, with tabular integration, what this is really used for is when we have to do more than one round of integration by parts. But I'm going to use it in this example to show you that we can, do it even though we don't have to do, successive rounds of it. In this column, what we want to do is continue to take successive derivatives until we get to 0. Okay. So here we know that the derivative of x is just 1. And we know that the derivative of any constant is 0, okay? And so by us getting to 0 here, this is what I mean by an integral to where if we do integration by parts, it terminates. The 0 here is basically telling us, hey, at some point, we're going to stop, okay? Now, we know that we need to take the antiderivative of e raised to the 2x dv. And if we do that, we know that we would just get 1/2 e raised to the 2x. If we did it again, we would get 1/4 e raised to the 2x. Okay. Now that we have that, how we actually perform the tabular integration in this case, since the derivative of u terminated as we did successive ones, we go diagonally across like this. And what we do here is we're going to put a plus, we're going to put a minus, okay? And so what we're going to figure out here is that the answer to this question is going to be this times this, which is going to be 1/2 x e raised to the 2x minus this times this. So this will be 1 times 1/4 e raised to the 2x. And then of course, since we're doing an indefinite integral, we do the plus c. Now what's happening here is that whenever we do the successive derivatives and successive antiderivatives, we're really following the same formula as the integration by parts formula. It's just that we're kind of doing it in abbreviated form here, okay? So now that we understand how this works, what we're going to do now is actually add on power here by 1. Instead of this being x raised to 1, we're going to let this be x raised to the 2. And then we're going to see how we could actually get this answer here. All right, so if we use tabular integration for this example, then we'll do u dv again, and we'll select x squared to be our u. We'll select e raised to the 2x dx to be our dv. If we do successive derivatives of, on x squared, we would have 2x, then 2, then 0. Because the derivative of x squared is 2x. The derivative of 2x is 2. Derivative of 2 is 0. Okay? Or any constant from that matter is 0. If we did successive antiderivatives here, then this would be 1/2 e raised to the 2x, and then 1/4 e raised to the 2x, and then 1/8 e raised to the 2x. Oh, and I just realized here that what this is, this was actually supposed to be for that. Yeah, because we saw that this answer was the same one as we had last time. So that's what this was for. And what I'm wanting to do now is actually show you what this is going to be. Yeah. So sorry if that confused you a bit there. Yeah, I wasn't supposed to have the squared on there. I was supposed to do it separately. All right, so again, we do the diagonals. We start off with plus and then just alternate signs, okay? And so I didn't mention this last time because it's not important for what we're doing now, but I'm going to go ahead and mention it because it'll be good for later. Notice that because this is 0 here, once we get to where we want to stop, of course you see how I'm doing diagonals across. At this point, we just go across here. And of course, I could put a minus there, and it's really not going to matter because 0 times anything is going to be 0. But this is going to be important to us whenever we face one of those types of integrals that I said was circular, meaning that what I choose for u and dv, both are not going to terminate, but it's going to be variation of a theme on themselves. And so being able to go across here when we see something similar to what we started with is going to be important. But I'm just going to, again, just draw this here to say, because this terminates, we go and look across, and that will let us know that that will be our last term, okay? Now, we've done this just like last time. We're just going to go across. So if we figure out what this is going to be, this is going to be x squared times 1/2 e raised to the 2x. So we'll just say 1/2 x squared e raised to the 2x. Pen is being delayed here. Let's try that again. Yep, still delaying. All right, and so next would be minus 2x times 1/4 e raised to the 2x. So that would be like 1/2 x e raised to the 2x. And then we'll have plus. And of course, 2 times 1/8 is going to give me 1/4. And then that'll be e raised to the 2x. And then, of course, the last term, when we look across, that's just going to be 0, okay? And, of course, ideally, we wouldn't want to write that. So I'm just going to erase it. And, of course, since this is an indefinite integral, we would do the plus c at the end, okay? And so this would be the answer to taking the integral of x squared e raised to the 2x. Okay. Now, traditionally, when we do integration by parts, what is shown is that we'll do integration by parts on something like this, and then we realize we got to do it again. And, you know, to me, it's just more efficient to do it this way. So that's why I'm coming out the gate and just showing you how to do it this way, because it really doesn't profit you a whole lot to be able to do successive integration by parts. When you can just do it via tabular integration, okay? All right, so let's go back and look at some more examples here. All right, so for our next example here, we see that we're asked to find out what is going to be the most general antiderivative of natural log of x squared, okay? So the first thing that we want to do to make life as easy as possible for ourselves is use our logarithm properties to rewrite natural log of x squared is just 2 times natural log of x, okay? And of course, if we do that, then we could rewrite our integral this way, okay? So now what we need to do is be able to choose what is going to be our u, what is going to be our dv, okay? So in this case, it turns out that the easiest thing to do here, and I'm going to switch colors here for a second, is if we let natural log of x be u, and I'm doing that because we know that the derivative of natural log of x is just 1 over x, so that's relatively easy. And if we take the antiderivative of dx, really 1 dx, if we take the antiderivative of any constant, it's just going to be that constant times x. And so the antiderivative of 1 dx is just going to be x. And so it's easy for us to take the antiderivative of 1 dx, easy for us to take the derivative of natural log of x. So because of that, we're going to make these choices here for our integration by parts. So we will say, let me switch this again. All right, let's go back to black here. All right, so therefore, we are going to say that the integral of, I wanted to put the 2 on the outside. All right, so 2 integral of natural log of x dx, which is going to be the same as 2 times integral of u dv, is going to be 2 times u v minus integral of v du. Okay. And here, if we know u is natural log of x, then du is going to be 1 over x. And if dv is equal to dx, then that means that v is just going to be equal to x. And so here, that lets us know that we're going to have 2 times, and then u and v, so it's going to be x times natural log of x minus integral of v, which is x, du, which is 1 over x, and this should be really 1 over x times dx here. Okay, and we know that because if I take the derivative of u with respect to x, that's just going to be 1 over x if u is natural log of x. And if we multiply both sides by dx, we end up getting this. So now that we have this, then this means that 2 times the integral of natural log of x dx is just going to be 2 times x times natural log of x. Of course, these x's here will just reduce to 1. So we just have 1 times dx. And of course, the antiderivative of 1 dx is just going to be x. So we'll have 2 times natural log of x minus x, and then all that plus c. And so what this ends up being here is that, and I'll go ahead and write this back in the original way that we had it. This means that the integral of natural log of x squared dx is just going to be 2x times natural log of x minus 2x plus c. Okay. And one of the things that we should glean from this, that will be very useful to us later, is the fact that we know that the antiderivative of natural log of x will just be x times natural log of x minus x. Okay. And so you'll see this at times in the future, especially if you are taking higher math courses. So this is a good one to remember. And if you can remember this, then you'll obviate the need to have to go through integration by parts to do it. But this would be the answer to this particular